Hello everyone, and welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. So today I thought we could take a look at two circuits that can, in certain circumstances, replace a Zener diode. Now, if we need something like a Zener diode, but we don't want or we cannot use a Zener diode, well, then we have some options. A much better option would be to use an integrated circuit like TL431. It's been quite often talked about on other YouTube channels, so I won't be talking about it. I will just mention that TL431 or anything like that, because there are all sorts of other variants with different prefixes, but also with 431 at the end. They are sophisticated integrated circuits that can be seen somewhat like an adjustable Zener diode. Okay, though they have 3 pins, a cathode, an anode, and a reference pin or an adjustment pin, and they can work just like a Zener diode, but with adjustable voltage and much better characteristics. Now, if we cannot use either of these, neither a Zener diode nor a TL431, we still have some other options available. I will show you in this video 2 of these 3 other options, and the third option I will leave it for another video because I haven't tested it yet. I thought about it, I simulated on a computer, but I haven't actually tested it on a breadboard. So I will want to talk about that at a later point in time. I will be talking about the simplest 2 options that we have in order to basically obtain something like a Zener diode that has some options to be adjusted. Okay, the simple option would be to take an NPN transistor. Of course, we could work with a PNP transistor as well, but it's easier to understand the mechanics with an NPN transistor. And to connect either 2 resistors in series or a potentiometer to all of the 3 pins. The idea is to create voltage divider. Basically, the middle point of the potentiometer is connected to the base of the transistor, and the other extreme ends are connected to the collector and to the emitter. This way, the collector becomes the collector of an NPN transistor becomes the equivalent of a Zener cathode, and the emitter becomes the equivalent of a Zener anode. If we have such a circuit, then we have the following situation. Basically, the entire voltage across the transistor, so the collector to emitter voltage, gets to be divided by this potentiometer and fed into the base of the transistor. Therefore, once the base emitter voltage reaches a certain value enough to turn on this transistor will tend to turn on, and therefore take its collector and drag it down closer towards the emitter. But in doing so, it will automatically lower the voltage across the potentiometer, and therefore it will automatically lower its base emitter voltage, which will make it tend to block itself or turn off, which will have the exact opposite effect. So essentially, there's going to be a single stable point in which this transistor can stay, and it will stay sort of like partially open, partially closed, and at that stable state it will have a certain collector to emitter voltage, and therefore it will be similar to a Zener diode that keeps a certain voltage across it. Okay. We can also place rectifying diode or perhaps even a Schottky diode in anti-parallel with this circuit, so that we can basically protect the circuit against reverse currents. Okay, and at the same time make sure that the circuit works as a Zener diode in reverse as well, because let's remind us a little bit. A Zener diode works in reverse polarity, okay, with a cathode connected towards the positive polarity and the anode towards the negative polarity. But if we connect the cathode to the negative and the anode to the positive, then a Zener diode will behave just like a rectifying diode, and it will keep only about 0.6, 0.7 volts across it. Okay, so in order to have this behavior as well with our circuit, we need to add a rectifying diode or a Schottky diode in anti-parallel with this. Okay, we can basically define a certain formula to determine the voltage of this well, pseudo diode, but it's in reality the behavior of the circuit will vary a lot based on the value of this potentiometer or of the two resistors that make up the voltage divider, and also various parameters that are associated with this transistor. We will go soon to the workbench and I will show you exactly how these circuits behave. But at least for a general theory, we can say that the total voltage will be about 0.7 multiplied by the total potentiometer value divided by the value of the resistance of the potentiometer between the base and the emitter of the transistor. Okay. In other words, to take a practical example, if this potentiometer is set at exactly at the middle, okay, when we will have a 0.7 volts base emitter voltage, we will also have a 0.7 volts collector to base voltage, and therefore we will have a total of 1.4 volts across our entire circuit. And therefore, we could say that it works like a 1.4 Zener diode. Okay, if the resistance from the base to the collector is twice as much as the one from the base to the emitter, then similarly we will have about 2.1 volts across the entire circuit, because then we need to have about 2.1 volts in order to have 0.7 volts base emitter voltage, and so on. Okay. Now, this circuit is simple, but it's not so efficient, it's not so good. It does work, but it typically needs quite a lot of current in order for the voltage to remain stabilized at what value we want, and we will see that on the curve tracer soon. Now, an enhanced version I found on the internet is this one with two transistors, one NPN, one PNP. It's similar to the first, I mean, as a way of working is identical, but the first transistor, the NPN transistor, does not get to be the one that pulls the entire voltage down. Instead, the NPN transistor's role is just that of opening the PNP transistor, and the PNP transistor is the one basically performing the voltage regulation. okay? I found this circuit on the internet with these two resistors of 10 kilo ohms each, but of course they could have different values, and also they could not only that they could both have different values, but they could have different values one relative to the other. In principle, if we have lower resistances, it means that T2 will open up faster, and also if R2 is smaller than R1, transistor 2 will also tend to open up faster. Okay, and we also have the anti-parallel rectifying diode to offer protection, basically. We will soon go to the workbench and see that this circuit performs a bit better than this other circuit. So these are the two simplest ways we can use transistors, in this case bipolar transistors, but theoretically we could create something like this with MOSFETs as well, in order to go around situations when we don't have a Zener diode available, or when we just don't want to use a Zener diode. Okay, this is particularly good when we are trying to work with components that we recovered from old devices. It is most likely that we haven't found that many Zener diodes because they are not really all that frequently used. So it's most likely that we will be able to recover a lot more transistors than Zener diodes. Okay, so such circuits definitely have this advantage of being able to easily replace that Zener diode. Anyhow, I will make this circuit, these circuits a little bit smaller and put them in a corner, so that I can come on top of them with a window that shows us the desktop of my curve tracer. It's a handmade curve tracer, but nevertheless it's good enough. I will shortly go to, I will soon go to the workbench, and I will start using this curve tracer, and I will show you various things that I will do. But before that, let's talk about what we see on the screen. So we have a graphic. You can think of it similar to, you know, the graphics that you were taught about in elementary school, in high school, in mathematics, right? Whenever you had, I don't know, so a function that you needed to understand how it behaves, that teacher would probably draw a graph on the table, on the blackboard. Anyway, we have the 0 point here exactly in the center because we have both positive and negative values on both axes. And what we will take a look at is going to be the so-called IV curve. We don't really call it V. For voltage we use the letter U, not V. V is just for volts, not for voltage as well. But anyway, it's the same thing. So basically we will be inserting a certain current in these circuits, and this current will be represented on the vertical axis. We will be having 2 milliamps per division, per vertical division. So we will be having a maximum of 30 and a minimum of minus 30 milliamps. But of course, minus 30 doesn't mean anything but the fact that we have flipped the polarity of the current going through the circuit. And on the horizontal axis, we have the voltage across this circuit, and we have 1 volts per horizontal division, so plus minus 15 volts. Okay. So that's what we are basically seeing on the screen. And now I will go to the workbench and step by step I will do various things, and I will show you how a Zener diode works, and then how the first circuit works, and then how the second circuit works. It's necessary for you to understand their behaviors in order to know what to change, and also if they are good enough for your projects or not, because, well, what you get is not quite right, it's not quite what you need. Okay, so let me just go to the workbench and we'll start making this experiment. Okay, so let me disconnect this now, and I will connect the BZX55 Zener diode that has 5.6 volts nominal voltage. Just a second. Okay, and we need to allow the screen to clear old graphics and to get to the new graphics. Okay, so this is the current to voltage curve of a regular Zener diode. Okay, a 5.6 Zener diode. We see on the horizontal that basically we have about 5 point something volts, between 5 and 6. And here, let me put a cursor exactly when the diode starts to work. Okay, so I cannot be super precise, but you understand. So somewhere around 1 milliamp, between 0 and 1 milliamp of current, the Zener diode cannot really work properly, so it will have a voltage based on different characteristics. It will typically track the voltage that gets applied to it. This is why we see an almost straight horizontal line. Okay. Beyond 1 milliamp, the Zener voltage starts to work, and then we have an almost straight vertical line. That means that between 1 and the maximum on my curve tracer for this diode has been 21 milliamps. Between 1 and 21 milliamps of current passed through the Zener diode, the voltage has barely increased with below 1 volt. Okay, so the Zener voltage keeps its voltage, the Zener diode keeps its voltage across it pretty much constant. Okay, and this is how a good Zener diode works. We also see, I'm gonna move the cursor so that we can just see the graphics better. We also see that below 0 amps, so basically in the reverse polarity, the voltage keeps, the Zener diode keeps only about a volt, less than a volt across it. Okay, I have some distortions at the bottom of the screen, which are about 1 volt, but anyway, we'll just ignore them. So this is how a normal Zener diode works, and try to make a mental picture of this graphic. Okay. Because we will take it as a reference point. This is how an actual Zener diode works as a discrete component. So now I will I will connect this curve tracer to the first circuit that I've shown you, and I will mount a 25 kilo ohm potentiometer in this circuit, and we will actually put a 25 kilo ohm potentiometer, we will play with it, and then we will put a 2.5 kilo ohm potentiometer and play with it, and we'll see how they differ. Okay, so with a 25 kilo ohm potentiometer, if I adjust it to the maximum, so basically if the middle point of the potentiometer gets connected to the collector of the transistor, we are essentially using the transistor as a simple rectifying diode. We are using the base emitter junction as a simple rectifying diode. And therefore, this is exactly what we see on the screen. The output voltage is below 1 volt. Okay? If I drag the middle point of the potentiometer down, then we see that at some point the transistor turns on slower, right? Because the total voltage needs to be higher in order for the transistor to turn on, and we start to see a curve on the screen, which is quite round. It tends to be quite round, and I'm going to bring the middle point of the potentiometer further down towards the emitter, and you will get to see how you know, this curve changes. The more I bring it to the emitter, the slower, the higher voltage the transistor needs in order to turn on, and therefore theoretically the higher the equivalent Zener voltage is. Well, practically it's not really like that, not that much like that. There are various non-linearities in the circuit, and at some point we have this weird behavior going on. The more we drag the potentiometer down towards the emitter, at some point this phenomenon happens that between 0 and about 2 milliamps, these are about 2 milliamps actually, right? The whole circuit pretty much tracks the voltage applied to it. And then it starts to work, but it starts to drop. The more the current increases, the more the voltage starts to drop. Okay, so when the circuit actually starts working, its output voltage is about, I don't know, 9.5 volts. But when the voltage gets stabilized to a certain degree, and we have 17 milliamps of current passing through the circuit, the whole circuit has stabilized at about 7.2 volts, which is considerably lower than those 9.5 we had earlier. So obviously you need to take these sort of things into consideration when you decide to work with this circuit. Okay, I've brought the potentiometer lower even more, but I kind of made a short circuit to the emitter, and now I brought it higher a bit. Basically what I'm trying to say is that I'm just showing you these things, you know, for educational purposes, but when you will actually need to use such a circuit in your practice, you will have to perform your own experiments in order to see the actual behavior of your circuit, and then draw the conclusion whether it is usable for you or not. Okay, now let's see, let's demonstrate the fact that if we decrease the value of the potentiometer or of the two resistors that form that voltage divider, we are essentially, at least for this circuit, we are essentially improving the response of the circuit. So I'm going to set this potentiometer to exactly the middle, or very close as possible to the middle point, so that the base emitter junction will get to receive half of the collector emitter voltage. Okay, and we have this curve on the screen, and I'm going to put the two cursors, one when one when the diode, well, the circuit starts to work, and the other when the circuit has well, in my case, when the circuit has basically stabilized to a relatively constant voltage. Okay, and what I'm going to do is essentially remove this 25 kilo ohm potentiometer and put a 2.5 kilo ohm potentiometer, which is basically 10 times smaller than this one. So now try to make a mental picture, try to memorize, you know, the image that you see here now, so that you can compare it with the image of the smaller value potentiometer. Okay, so I've removed the first one, and just a second, it's a bit tricky to, okay. And now let me adjust it to precisely the middle point, precisely 50%. Okay. So now the potentiometer is set, I have a 2.5 kilo ohm potentiometer, 10 times less than the previous one, which is also set exactly at half. So we have the exact same position, but lower value. Theoretically, that should mean that the circuit will give us in the end the same voltage, but practically we see that now the circuit, well, the transistor turns on a lot faster, a lot sooner, and therefore the response tends to be a lot more linear than the previous response, and the final voltage gets to be much smaller, like less than half of the final voltage that we managed to get in the previous case. Okay, so we can clearly draw the conclusion that it's not only the ratio of the two resistances that matter, but also the resistances themselves, because they, at least with a bipolar transistor, they dictate how much current gets to be fed into the base, and therefore how fast and how much the transistor will turn on. Now let's play a little bit with this potentiometer as well. I'm going to move the cursors so that they don't bother us. I'm going to turn this potentiometer up to the maximum. Just like before, we see that the output voltage is less than a volt, because again we're basically short-circuiting the base of the NPN transistor to the positive input of the entire to the collector, right, which is also the positive input of the entire circuit. So we're basically using the base emitter junction as the simple rectifying diode. And now I'm going to start slowly turning this potentiometer down, and we will see that the output voltage will start to increase, but it will not increase you know, so suddenly. There will be a certain slope associated with it. Basically, the more current we will be feeding into the circuit, the more this voltage will increase. Okay, and now I'm at a pretty much maximum possible, at least for this potentiometer. We also see that we have a linear increase in voltage as the current increases linearly. Okay, we don't have this straight zigzag that is typical to a good Zener diode. And these are basically the limitations of having just a single transistor for this kind of job. Now let's move on and connect the second circuit. and take a look at how better it is the second circuit with 2 transistors. Okay, let me connect the 25 kilo ohm potentiometer, because right now there's nothing connected. Okay, and let me adjust it to the maximum. So now we see, well, just like before, the minimum voltage is somewhere below 1 volt. It doesn't surprise us. So I'm going to bring the middle point of the potentiometer down towards the emitter, and we will see that this voltage, this total circuit voltage, will get to increase a little bit, but sadly we have lost a certain linearity. Now I have to drag the potentiometer quite a lot in order to see even small differences. The circuit is used better if the potentiometer is not put across the entire voltage, but only, I don't know, between the base and the emitter, perhaps, you know. Anyhow, I'm going to drag it down a little bit more soon. Okay. And now we see a new response, and drag it down a little bit more. And now we see a new response, and so on and so forth. So basically we see that the circuit with 2 transistors works a lot better than the first one, and behaves a lot closer to how a Zener diode works, to how an actual discrete component works. Okay. We have much straighter zigzag lines, and the total voltage is a lot more constant. So now let's do the exact same experiment. I'm going to set this potentiometer to exactly 50%. Let's see, about here. Okay, and we will wait for the screen to refresh, and I will put the 2 cursors just like before. One when this slope starts to go up, and one when it has ended, kind of like that. Okay. And now I'm going to remove this 25 kilo ohm potentiometer and put the 2.5 kilo ohm one, which we've seen in the previous circuit. It gave quite a big it made quite a big difference. It gave quite different results, and I'm going to adjust it to 50% as well and allow it to refresh. And now we see that we basically have the same result, more or less. It's pretty much the same curve, the same slope. The voltage remains pretty much as constant with the 2.5 kilo ohm potentiometer as with the 25 kilo ohm one. So in other words, for the second circuit, the value of the potentiometer or of the voltage divider resistors that we may have in place of the potentiometer doesn't matter all that much, because we have 2 transistors working together. So basically the amplification factor of only 1 transistor doesn't matter all that much. Okay, so that's pretty much it. I hope you found something useful, something that you did not knew before, and I hope you now know how you can basically make up for not having a Zener diode with just a few simple components that you can easily salvage from old devices. So thanks a lot for watching this video. Don't forget to like and subscribe, especially if you plan to come back in the future. I'm trying to constantly make new videos about electronics. Also, please consider supporting me on Patreon. The faster I can buy components and devices, the faster I can learn new things, and the faster I can come here on YouTube and teach you as well, so that you don't have to spend so much time and energy learning and studying these things and performing experiments as I need to. Thanks a lot for watching. I'll see you soon in the next video. See ya.